Welcome to number 6 in this series of short videos on statistical process improvement and statistical quality assurance. We're now talking about the interaction of measurement and basic statistical methods. We've talked a bit about using the basic t-interval for a mean and the basic chi-square interval for standard deviation, and have made 2 applications of that. In this module, we're going to present 2 more applications of those one-sample formulas with the basic objective here to illustrate the basic insight that how physical variation, sources of physical variation interact with data collection, governs what can be learned from a data set, and in particular how measurement error is reflected in that data set. And so for a next application of these one-sample methods, we're going to consider a situation where one has many similar measurement devices that could potentially be used to do measuring. The most common kind of application of this would be where one has a number of different operators that could use the same physical piece of equipment to produce a measurement. And so the combination of that single piece of equipment with different operators, according to the way we're using the language, would constitute different devices. That is, the devices in this case, differences between them are differences between human operators. We might illustrate this with a schematic where there is a single measurand that gets measured by several different devices to produce n different measurements, where now we're going to assume that every device has the same standard deviation associated with it, but that different devices have different biases. In this kind of a setup, in this kind of a context, the individual measurements might be described or modeled as independent, with mean value, that is the measurand, plus now an average bias. So this mu sub delta is standing for an average bias, and the variability that one sees in these y's is governed not only by how big is the sigma device or sigma squared device, but also how variable are the biases. And so we have here a sigma squared sub delta. In this context, and so there's a discussion here on panel 6 as to how this comes about, that I'll leave for your careful reading when we're not talking here. But basically, observations y have mean, measurand plus average bias. Observations y have variability that is governed by how variable the biases are and how variable are measurements for a single device. In this kind of a context where different devices are really different operators, there's a standard kind of language that gets used. People talk about R&R, repeatability and reproducibility. And this combination of operator bias, variability, and repeatability and repeat measurement variability gets called sigma R&R. The R&R variation, the repeatability and reproducibility variation. That is this funny looking square root of sum of variances in this context has a important and interpretable meaning. While typically this mean that is measure n plus average bias is less interpretable. So this is a context where the standard this funny looking standard deviation actually has carries real interest. And so in that case, the t-interval is not so interesting, but rather the chi-square interval is probably more important because it helps quantify so-called R&R, repeatability and reproducibility variation. A second kind of application of these one sample t and chi-square intervals comes about this way. If one has two devices and a number of different measurands and thinks about measuring each measurand once with each device, one gets a schematic something like this. So here measurand 1 goes through device 1 to produce a y. It also goes through measurement device 2 to produce a y. Measurand 2 goes through device 1 to produce a y, through measurement device 2 to produce a measurement. And then these paired measurements that go with each one of the individual measurands can be thought of as producing differences. If you take the device 1 measurement and subtract the device 2 measurement, those differences have average, that is the difference in the two biases, so it's this delta 1 minus delta 2, and have standard deviation, that is the square root of the sum of the squared device standard deviations. That means that if one applied the t-interval based on d bar and s, one could estimate this difference in biases between the two devices. That's the more important of the two quantities, and the t-interval allows us to get at that difference in device biases. And this slide lays that out and says apply the t-interval to differences, taking d bar plus or minus ts over root n. Root n is the number of measurands here. So one has twice n measurements, but only n measurands. So here are yet two more applications of the basic one sample statistical methods where one takes account of measurement variation, measurement noise.